Never trust client-side validation. Opening the illusion at the edge. There is a moment in every security engineer's career where they look at a piece of code, a form field, or a browser submission and realize, with a slow and slightly nauseating clarity, that everything they thought was protecting a system was actually protecting nothing at all. The form had validation logic. The JavaScript was well written. The UI refused to let users type negative numbers into a quantity field or submit an empty email address. It looked secure. It felt secure. And then someone opened a browser's developer tools, disabled the JavaScript, and sent whatever they wanted directly to the server. That moment is the lesson this session is about. Never trust client-side validation is not a beginner tip that you absorb once and then move past. It is a foundational philosophy about where trust belongs in a system and why the location of a control determines its actual value. The phrase sounds simple. The implications are not. They reach into data pipeline design, into API architecture, into compliance frameworks, into the way you write database schemas and build authentication systems. They reach into every decision about where a system decides to believe what it is being told. The question this session is asking is not, did you validate the input? The question is, did you validate it in a place where the attacker cannot reach the validator? Everything else follows from that. The foundation, what validation actually is and where trust lives. Before anything else, you need a clear understanding of what we mean by validation, because the word gets used loosely, and that looseness creates dangerous assumptions. Validation is the process of checking whether input meets a set of defined requirements before allowing it to affect a system. Those requirements might be structural. Is this a valid email address format? Is this a number between 1 and 100? Is this a date in the past? They might be business logic requirements. Does this user have an active account? Is this product in stock? Does this transaction total match the line items? They might be security requirements. Does this string contain SQL syntax? Does this file claim to be a JPEG but contain a PHP script? Validation is not the same as sanitization. Sanitization transforms potentially dangerous input into something safe, encoding HTML special characters so they render as text rather than executing as markup. Validation decides whether input is acceptable at all. Both matter. Both must happen on the server. But they are different operations with different goals, and a system that confuses them ends up doing neither well. Client-side validation is validation that happens in the browser, or in a mobile application, or in any environment that is under the control of the end user rather than the service provider. The browser's JavaScript can check that a form field is not empty. A mobile app can verify that a phone number is the right length before submitting it to a server. These checks are genuinely useful, but only for one purpose: improving user experience by giving immediate feedback before a network request is made. They are not security controls. They never were security controls. They cannot be security controls because the entity being asked to enforce the rule is the same entity that might want to break it. Server-side validation is validation that happens in an environment the user cannot touch. When a request arrives at an application server, it arrives stripped of any promise that the browser made on its behalf. The server sees raw input. It does not know whether the browser validated it, rejected it, transformed it, or whether the browser was involved at all. A request can be crafted entirely in a command line tool like curl or a proxy like Burp Suite, and sent directly to the server endpoint with no browser in the loop. If the server assumes that because the browser validated the input must be valid, the server has made an assumption that any attacker with a network connection and 15 minutes of familiarity with HTTP can violate. This is the core principle, stated plainly. The browser cannot be trusted because it is on the attacker's machine. Any control that lives entirely in the browser is a control that can be removed, bypassed, or modified by the very person it is meant to constrain. The structural tension, usability, performance, and the temptation to trust the front end. There is a real and honest tension at the heart of this principle. Client-side validation is genuinely valuable, and the pressure to rely on it is not entirely irrational. Understanding that tension is what allows you to navigate it correctly. When a user fills out a registration form and submits it, a round trip to the server to validate the email format takes time. It consumes server resources. It creates latency. The user waits. By contrast, a JavaScript function that checks the email format in under a millisecond and highlights the field red before the user even clicks submit is a genuinely better experience. For the majority of users who are not trying to attack the system, that immediate feedback is helpful, efficient, and appreciated. Development teams under deadline pressure look at this and ask a reasonable question. If the JavaScript is already checking this, why do we need to check it again on the server? Is that not redundant? It is redundant in the same way that a lock on a bank vault is redundant if there is already a sign outside that says, "Please do not steal." The redundancy is the point. The two checks serve different populations with different intentions. Client-side validation exists to serve honest users efficiently. Server-side validation exists to protect the system from everyone, including dishonest users who have bypassed or ignored the client-side check. These are not the same population, and they are not the same check, even if they implement the same logical rule. Treating them as interchangeable is the mistake. There is a second source of tension that is worth naming. As applications have grown more complex, and the front end has taken on more responsibility, single-page applications built in React or Angular or Vue, mobile applications with their own local logic, third-party integrations that send data through non-browser paths. The distinction between client and server has become blurrier for development teams. When the front end is doing significant data transformation, business logic, and state management, the temptation to treat it as a trusted participant in the system grows. The front-end developers know their code is correct. They trust their validation logic. They are offended by the implication that it might be circumvented. This is where the principle gets uncomfortable to defend, because the answer is not that the front-end code is poorly written or untrustworthy in the moral sense. The answer is that no matter how well the front-end code is written, it runs in an environment the server cannot control, and therefore the server cannot rely on the guarantees it makes. A developer's confidence in their own code is not a security control. The server must validate independently, always without exception, as if the client had done nothing at all. The architectural philosophy, designing systems that enforce this at every layer. Once you accept the principle, the question becomes architectural. What does a system look like when it is designed with never trust client-side validation as a governing rule? The most important design decision is where the validation logic lives. In a well-designed system, validation logic on the server is not an afterthought or a duplicate of the client logic. It is the authoritative specification of what the system accepts. The client-side validation is derived from this specification, a translation of the server's rules into a form that the browser can execute for user experience purposes. But the source of truth is the server. This has an immediate implication for API design. Every API endpoint must be designed as if it will receive arbitrary input from an untrusted caller, not just a slightly wrong input from a mostly trustworthy user. Arbitrary input, crafted input. Input designed to confuse the parser, overflow the buffer, inject SQL, or manipulate the business logic. The API does not know whether the call came from the official front-end application or from a custom script. It must behave correctly regardless. Input is evil until proven otherwise, a related principle that sits just downstream of the one we are studying here. When a string arrives at an application, the correct posture is to treat it as potentially hostile until validation clears it. Not neutral, potentially hostile. A file upload that claims to be an image must be validated as an actual image. A JSON field that should contain an integer must be checked to confirm it contains an integer and not a string with a SQL fragment inside it. A date field must be parsed as a date rather than trusted to behave as one. The database layer is where this principle becomes life or death. Parameterized queries, the practice of separating SQL structure from SQL data, exist precisely because of this principle. When you build a SQL query by concatenating user input directly into the string, you are trusting the user to provide data that behaves like data and not like SQL commands. SQL injection is old. It is well understood. It appears in the OWASP top 10 every year. And it is still one of the most prevalent attack vectors in the wild, because teams still build systems that trust the client to not send SQL syntax in a form field. Whitelisting is stronger than blacklisting in this context, and the reason is that blacklisting shares the same assumption as client-side validation, that you know in advance everything that is dangerous and can enumerate it. You cannot. Attackers are creative. Encoding schemes are numerous. There are ways to express the same character in dozens of different representations. A blacklist that rejects script will miss SCR\X69PT. Whitelisting, accepting only what you have explicitly defined as acceptable, turns the problem around. Instead of asking, "Is this dangerous?" you ask, "Is this one of the things I know are safe?" Everything else is rejected by default. This is not always easy to implement for rich, varied input, but the principle guides the design. For structured data, email addresses, phone numbers, currency values, UUIDs, whitelist validation is entirely practical. For free text fields that genuinely need to accept arbitrary content, the focus shifts to sanitization, output encoding, and treating the content as untrusted data at every subsequent rendering point. Tools that enforce this principle and the trade-offs each one carries. Every tool that enforces input validation does so at a particular layer and with a particular cost. Understanding what each tool actually enforces and what it leaves open is the difference between a developer who knows about these tools and a practitioner who knows how to use them. A web application firewall sits upstream of the application and inspects incoming HTTP requests for known attack patterns. It can reject requests containing SQL injection strings, cross-site scripting payloads, and command injection sequences. It is genuinely valuable as a compensating control and as a first line of defense. But it is not a replacement for server-side validation, and understanding why reveals something important. A WAF is a blacklist at the perimeter. It knows about the attack patterns that were documented when its rules were written. It does not understand your application's business logic. It cannot know that a particular field should only ever contain a 4-digit year, or that a quantity field should never be negative. A WAF that blocks drop table in a URL parameter will not catch a business logic manipulation where a user changes their order quantity from 1 to -1 and receives a credit to their account. Server-side validation is the only layer that understands what the application is supposed to accept. The WAF is an additional layer, not a substitute. A static application security testing tool analyzes source code without executing it, looking for patterns that indicate security vulnerabilities, calls to deprecated functions, unsanitized input reaching SQL construction code, missing validation checks before data flows into sensitive operations. SAST is powerful because it finds vulnerabilities at the code level before the application is deployed. The trade-off is false positives and the context blindness of static analysis. A SASD tool that flags every string concatenation near a database call will overwhelm developers. A well-tuned SASD tool integrated into the CI/CD pipeline and configured to match the language and framework in use catches real violations before they reach production. But SASD is a development time control. It finds what developers forgot to do. It does not enforce anything at runtime. A runtime application self-protection tool embeds into the application itself and monitors its behavior during execution. When an input triggers an operation that the application should not perform, a SQL query built from unsanitized input, a file read that traverses outside the intended directory, the RASP can block it in real time. The difference from a WAF is that RASP operates inside the application, with access to the full execution context. It knows that this particular function received this particular input and attempted this particular operation. The cost is performance overhead and the complexity of integration. RASP requires deep knowledge of the application runtime, careful configuration, and ongoing maintenance as the application evolves. But for applications where a missed injection could be catastrophic, the overhead is justified. A tokenization gateway is the tool that materializes the client-side validation principle most directly in a data context. When a user submits a payment card number, the tokenization service intercepts it and replaces it with a meaningless token before it reaches any application database. The application never stores the real card number. It stores something that looks like a card number, can be referenced in the same way, but means nothing to an attacker who exfiltrates the database. The server never trusted the client to send a safe representation of the card number. It took the card number out of the system entirely and replaced it with a surrogate. This is the principle in its most elegant architectural form. An API schema validation layer enforces the structure of incoming API requests against a defined schema, an open API specification, a JSON schema document, or an equivalent. Before any application logic runs, the framework validates that the request contains the required fields, that each field contains the correct data type, and that values fall within defined ranges. This is whitelist validation at the API boundary. It does not require the application developer to write validation code in every endpoint function. It centralizes the enforcement and makes it auditable. The trade-off is that the schema must be kept current with the application's actual behavior, which requires discipline, tooling, and a development culture that treats the schema as authoritative rather than aspirational. A secret scanning tool does not validate application input directly, but it enforces a related principle, that credentials and secrets should never be present in client-accessible code. Hard-coded API keys in JavaScript that get served to browsers, tokens embedded in mobile application binaries, connection strings in front-end configuration files. These are all forms of trusting the client not to extract and misuse what it finds. Secret scanning in the CI/CD pipeline catches these violations before they ship. The cost is integration time and occasional false positives. The alternative is discovering, months after deployment, that every user who opened developer tools in their browser has been looking at your database connection string. Implementation depth, building the right controls at the right layer. Consider the task of building a data ingestion pipeline for a security analytics platform that receives event logs from multiple external sources. Some of those sources are trusted internal sensors. Some are third-party integrations whose code you do not control. All of them send JSON payloads over an authenticated API. The naive implementation validates input on the client side by providing an API specification document and relying on the sending application to conform to it. This works fine for the internal sensors, which were built by the same team and follow the spec correctly. It works less well for the third-party integrations, whose developers interpreted the spec differently, Used null where the spec requires an empty string, omitted optional fields entirely, or occasionally sent arrays where the spec requires objects. The correct implementation defines a JSON schema for every expected payload type and validates every incoming request against the schema before allowing it to proceed to the processing stage. Requests that fail validation are rejected with a structured error response that tells the sender exactly which field failed and why. This is not just security, it is operational hygiene. Malformed data that passes into a pipeline without validation causes failures downstream that are hard to diagnose and hard to trace back to their origin. But schema validation is not sufficient on its own. The schema can confirm that a field contains a string. It cannot confirm that the string does not contain a SQL injection payload if that string is eventually used in a database query. Server-side sanitization and parameterized queries must follow the schema validation as independent steps. The layers are additive. Each one handles a different category of problem. Now consider the governance requirement. In a GDPR-compliant data pipeline, personally identifiable information must be handled with documented controls at each processing stage. The validation layer is a processing stage. The decision to reject a record because it fails schema validation, to quarantine it for manual review, or to strip the PII field and process the rest. Each of these is a processing decision that must be documented in the data processing agreement. The security control and the compliance requirement are not separate tracks. They are the same architecture, viewed from different angles. A practical implementation decision that often gets overlooked is what to do with validation failures. Failing loudly to the sender, returning a 400 status with a detailed error message, is the right approach for legitimate senders who made an honest mistake and need to correct it. But it can also be a reconnaissance gift to an attacker who is probing the API to understand its validation rules. The error message that says, field quantity, must be a positive integer, confirms to an attacker that they have found a quantity field worth targeting, and tells them exactly what constraint they need to satisfy to pass validation for everything else. Rate-limiting validation failures, alerting on patterns of repeated failures from the same source, and providing error messages that are informative for legitimate callers, but not a complete map of the validation logic, are all implementation decisions that require judgment about the expected caller population and the threat model. When the principle is violated, 3 failures worked through from symptom to root cause. The first scenario. A retail application's shopping cart allows a quantity of -1 to be submitted, resulting in the price of the item being subtracted from the order total rather than added. Users discover this and exploit it to receive large credits. The application developer is confused because the front-end form field has a min attribute set to 1, and the JavaScript validation function rejects any non-positive quantity before allowing the form to submit. Working through the diagnosis begins with reproducing the behavior outside the intended client. When you capture the post request to the cart endpoint using a proxy and replay it with quantity set to -1, it succeeds. The server accepted the value. The next question is where in the server-side code the quantity value is used. Tracing the execution path reveals that the cart calculation function receives quantity directly from the request body and uses it without validation. The assumption was that the form's front-end validation guaranteed the value would always be positive. The JavaScript validation did exactly what it was designed to do. The server simply did not participate. The fix is straightforward to describe and sometimes uncomfortable to implement at scale. Server-side validation is added to every endpoint that accepts a quantity parameter. The validation checks that the value is an integer, that it is greater than 0, and that it does not exceed a reasonable upper bound that prevents unrealistically large orders from being submitted. The front-end validation remains in place for the user experience benefit. The server-side validation is now the actual enforcement. The two are no longer assumed to be equivalent. The second scenario, a web application allows users to upload profile pictures. The application checks the file extension client side. A JavaScript function inspects the file name and rejects anything that does not end in JPG, PNG, or GIF. An attacker uploads a PHP web shell with the file name shell, PHP, JPG. The extension check passes. The file is stored on the server in a publicly accessible directory. The attacker navigates directly to the file URL and executes commands on the server. The diagnostic path here moves through several layers. The front-end check only inspected the file name string. It did not look at the file's content, its MIME type as declared by the client, or its actual binary content. The server only checked the extension that the client reported. Neither checked whether the file was actually an image. The fix requires a fundamentally different approach to file validation. The server must read the actual binary content of the uploaded file and verify that it matches the structure of the claimed format. A JPEG file has specific magic bytes at its header. An actual PNG has a specific signature. A PHP script does not look like an image in its binary content, no matter what name it is given. The server validates the actual content, not the claimed content. Additionally, uploaded files should never be stored in a publicly accessible directory where they can be executed by the web server. They should be stored outside the web root, in a location from which they can only be served through an application layer that controls how they are delivered to the requesting browser. The third scenario. A security analytics platform's API receives threat intelligence feeds from multiple partners. One partner integration begins submitting records with an unusually large value in a field that represents the number of times an IP address has been observed performing suspicious behavior. A count field that should contain an integer in the range of 1 to several thousand. The partner sends a value of 9,999,999,999,999, which is technically an integer, but causes a downstream aggregation query to overflow and return incorrect results for dashboard metrics. The analysts notice the dashboard showing anomalous statistics, but cannot immediately identify why. The diagnostic process starts with the data. Querying the raw ingested records for that partner reveals the outlier value. Tracing it backward through the pipeline confirms it arrived in the request payload and passed schema validation, because the schema defined the field as type integer without specifying a maximum value. The schema was not wrong in a structural sense. It was incomplete in a business logic sense. The resolution requires understanding that validation is not only structural but contextual. An integer field that represents a count of observations has a meaningful upper bound defined by operational reality. No single IP address will be observed performing suspicious behavior 9 trillion times before the feed is updated. The schema must reflect this. Adding a maximum value constraint to the schema, chosen based on the operational range of realistic values rather than the theoretical range of the data type, catches this category of abuse. Separately, anomaly detection on incoming data volume and field value distributions provides a second layer that catches values that pass schema validation, but are statistically inconsistent with historical patterns from the same source. The role-based lens, 3 seats at the same problem. A security data engineer designing a log ingestion pipeline encounters this principle at the earliest and most consequential point in the data lifecycle. Every log source they integrate is a client. None of them can be trusted to send only what the schema expects, only the fields that matter, only values within sane ranges. The engineer who designs the pipeline with schema validation at the ingestion boundary with sanitization of string values before they flow into queries, and with rejection and quarantine logic for records that fail validation, builds something resilient. The engineer who trusts the source to send clean data builds something that will fail in ways that are difficult to debug, impossible to predict, and potentially dangerous when a malicious or compromised source begins sending crafted values. The specific implementation decision this role faces is where to place the validation. Performing schema validation before data enters any storage system means that malformed records never contaminate the clean data. It also means that rejected records must go somewhere, a dead letter queue, a quarantine table, an alert, and that there must be monitoring on the volume of rejections, because a sudden spike in rejection rate is either a bug in the source system or an indicator of something more deliberate. The pipeline that treats validation as a binary gate and discards failures silently is operationally blind. The pipeline that treats validation failures as signals worth examining is doing detection engineering at the data layer. A compliance and audit professional assessing a system's GDPR controls encounters this principle when examining pseudonymization and data classification. GDPR requires that personal data be accurate, which means the system must have controls that prevent incorrect or malformed personal data from entering the data store. Client-side validation alone does not satisfy this requirement in a way that would survive regulatory scrutiny, because the auditor understands and will ask whether the validation can be circumvented. Demonstrating server-side validation of PII fields with audit logs showing that validation was applied to every record is the kind of evidence that satisfies an auditor who is looking for systematic controls rather than aspirational ones. The auditor is also specifically interested in the mapping vault, the structure that links pseudonyms to real identities. Who has access to that vault? Are those access grants documented and periodically reviewed? Is there a validation layer that prevents unauthorized attempts to query the mapping, rather than relying on users to not try? A security architect designing a system that handles sensitive data faces this principle at the design phase, which is precisely the right time to enforce it. The decisions made at design time, where validation logic lives, whether it is centralized in a shared library or duplicated across endpoints, whether the data model enforces constraints at the database layer as well as the application layer, shape what is possible later. A data model where the database itself enforces type constraints, range constraints, and foreign key integrity is a model that provides a final validation layer even when application code has a bug. A database that accepts whatever the application sends because the application is trusted creates a situation where a single application layer failure means that the database receives and stores whatever an attacker can craft. The architect who enforces validation at the application layer and at the database layer is building defense in depth against input-based attacks. The architect who enforces it only at one layer is trusting that one layer to be perfect. The hard cases, when validation is genuinely complicated. Not every input validation problem is solved by a simple schema check. Some of the most consequential validation failures involve inputs that are structurally valid but semantically wrong. That is, they pass every format check but contain content that is harmful when the system acts on it. Consider a file processing service that accepts CSV uploads for bulk data import. The schema validation can confirm that the file has the right delimiter, the right number of columns, and the right data types in each column. It cannot confirm that a formula in a cell, something like equals system, CMD calc, EXC, will not be executed by a spreadsheet application if the data is exported to Excel later. This attack class, sometimes called CSV injection or formula injection, is not a failure of the CSV format itself. It is a failure to understand the downstream rendering context of the data. The validation layer must understand not just what the data is when it arrives, but what it will become when it is consumed. Output context matters as much as input format. Consider a web application that accepts a URL from users and fetches its content, a common pattern for preview features, webhook endpoints, or feed aggregators. The server-side validation might confirm that the input is a valid URL format. It might even check that the scheme is HTTP or HTTPS rather than file, // or JavaScript. But if the server fetches the URL from its own network without further restriction, an attacker can supply a URL pointing to an internal service. 169.254.169.254, the AWS instance metadata endpoint, or an internal admin panel, and cause the application to make requests on the attacker's behalf from inside the network perimeter. This is a server-side request forgery vulnerability, and it is a case where the validation of the input value misses the validation of the operational consequence of using that value. The fix is not only to validate that the URL is syntactically correct, but to validate that the destination is an acceptable one, blocking requests to internal IP ranges, restricting to known safe domains, or using a separate sandboxed fetch mechanism that operates outside the main network. These hard cases share a common pattern. The validation logic was written with the known attack surface in mind, and the attack came from a direction the validator did not consider. This is not a failure of effort. It is an inherent property of blacklist-based and pattern-based validation. The attacker's job is to find the case the validator did not think of. The defender's job is to reduce the number of such cases by using whitelisting, parameterization, output encoding, and defense in depth, making the cost of finding the unhandled case high enough that it is not worth the attempt. The scenario that brings it together: a pseudonymized research platform under pressure. A medical research organization has built a longitudinal study platform that tracks patient outcomes over 5 years. They followed the correct architecture for pseudonymization. Each patient is assigned a research identifier, a UUID generated at enrollment. Clinical data is stored against this identifier. The mapping between the identifier and the patient's real name and contact information lives in a separate vault system, managed by a small group of privacy officers, accessible only through a separately authenticated API that logs every access. The system has been running for 2 years when a new requirement arrives. A regulatory review asks the organization to demonstrate that patient data cannot be re-identified by anyone who gains access to the research database. The review is concerned specifically about the combination of demographic fields, year of birth, gender, and the name of the small rural hospital where the patient was enrolled, which together might uniquely identify individuals in a dataset small enough for cross-reference. The security architect is asked to assess the risk and propose controls. The first step is to understand the current validation posture. The research data entry interface has client-side validation that prevents the entry of obviously anomalous values, ages below 0, dates in the future for historical diagnoses. But the server-side validation checks only data types and required fields. It does not examine the combination of demographic fields for re-identification risk. A record with year of birth 1942, female gender, and a hospital with only 3 enrolled patients in that year is not invalid by any individual field rule, but it is potentially identifying when the 3 fields are considered together. The second step is to understand the upstream assumption that has been violated. The design assumed that pseudonymization was sufficient, that removing the real name and replacing it with a UUID made the data non-identifying. GDPR does not share this assumption cleanly. It treats pseudonymous data as still being personal data, because the link back to the real identity exists in the vault. And more practically, the combination of quasi-identifying fields creates a re-identification risk that the UUID substitution does not neutralize. The third step is to design validation controls that address the actual threat model rather than just the syntactic correctness of individual fields. The approach here is to implement k-anonymity checking at the data entry stage. Before a record is accepted into the research database, the server-side validation checks whether the combination of demographic fields that are retained in the research dataset, not the real name, but the quasi-identifying fields, appears in at least k other records already in the dataset. If the combination is unique or near unique, the record is flagged for review rather than automatically stored. The privacy officer decides whether the record should be entered with reduced demographic specificity, whether it should wait for more similar records to be enrolled before being committed, or whether the re-identification risk is acceptable given the minimal sensitivity of the particular data. This is not a lightweight control. It requires a live query against the existing dataset at enrollment time. It adds latency to the enrollment process. It creates a category of records that are in a pending state, which requires workflow management and communication with the clinical sites doing the enrollment. The trade-off is explicit. The organization is accepting operational complexity in exchange for a stronger compliance posture and a more defensible response to the regulatory review. The validation also extends to the mapping vault. The Vault's API accepts requests that include the research identifier and return the patient's real identity. Each request is logged with the requesting user's identity, the timestamp, and the justification code. But until now, the Vault API has only validated that the request is authenticated and that the identifier exists. It has not validated that the requesting user has a legitimate operational reason to access that specific patient's record. A privacy officer who queries the vault for every patient in the dataset, either through error or through curiosity, has been technically permitted to do so. Adding business logic validation to the Vault API changes this. The API now checks whether the requesting user is associated with an active investigation, consent withdrawal request, or adverse event report that requires real-world identity resolution. Requests outside these categories are rejected, not just logged. This validation is entirely server-side. There is no front-end enforcement because there is no interactive front-end. The Vault is an API consumed by other services, but the principle is the same. The constraint lives where it can be enforced, not where it is convenient to describe. The outcome of this architectural review is a platform that can demonstrate layered validation to the regulatory reviewer. The research data entry has server-side schema validation, server-side quasi-identifier combination checks, and server-side k-anonymity assessment. The mapping vault has server-side authentication, server-side access control, and server-side business logic validation of access justification. Each layer covers something the adjacent layer does not. No layer trusts a previous layer to have done the whole job. The reviewer can trace the controls set from data entry through storage, through identity resolution, and see a coherent defense at every point. The constraint in this scenario was the regulatory timeline. The organization had 8 weeks to implement the k-anonymity checks and update the Vault's validation logic before the next review. They could not rebuild the platform. They had to instrument the existing one. The k-anonymity check was implemented as a pre-storage validation hook in the data entry API, designed to be configurable so that the value of k could be updated by policy decision without a code deployment. This was a deliberate architectural choice. The validation logic itself must be maintainable, because the threat model it is responding to will change as the data set grows, as the regulatory guidance evolves, and as the organization's understanding of re-identification risk matures. Closing, the posture that outlasts any single threat. The lesson is not about forms and JavaScript. It is about where you place your trust and why. Every time you encounter a system boundary, a point where data moves from one layer to another, from a user to an API, from an API to a database, from a pipeline stage to a downstream consumer, that boundary is a place where the previous environment's guarantees end, and the current environment's validation must begin. You cannot carry guarantees across boundaries. You can only check for yourself. This posture is not paranoid. It is structurally honest. The client is on someone else's machine. The third-party integration was written by a team that understood your API specification differently than you wrote it. The partner who sends you threat intelligence feeds has no insight into the effects of their data on your aggregation queries. None of them can be malicious. All of them can be wrong. And the system that fails when confronted with wrongness it did not anticipate is a system that was built with hidden assumptions about the goodwill of every caller it will ever receive. The discipline this principle enforces is the discipline of designing for the actual world rather than the assumed world. In the actual world, input arrives in states the developer did not foresee. In the actual world, the front-end application is sometimes replaced by a proxy. In the actual world, a schema that was correct at launch has been modified by 15 engineers over 3 years, and not all of them knew about the original business logic constraints. In the actual world, the validation check that was meant to live at the server got moved to the client during a refactoring sprint and nobody noticed. What makes a practitioner reliable under pressure is not knowing every attack pattern. It is holding a posture that does not require knowing every attack pattern to provide meaningful protection. Validate on the server always, as if the client did nothing. Trust what you can verify in your own environment. Treat input as potentially hostile until it proves otherwise. Design the validation logic so that it is the authoritative source, not a copy of someone else's copy. That posture will serve you in the interview room, in the architecture review, in the incident post-mortem, and in every line of code and every policy decision you make for as long as you work in this field. End of session mental model. Never trust client-side validation.